going to explain transformational variables. We go over transforms. And mainly the Jacobian thing. Maybe the questions like why absolute value is the easier one. This is kind of the high dimensional analog, so I'll allude to that. But I'll show you where it comes from. I.e., why maybe it's not this thing. Okay. Can we go over transforms? I will go over it. Thought about it for a minute or two because you asked me earlier, so I was able to think about it as I was doing dishes at home and things like that, so I appreciate it. Yes. Second one was, can we solve this thing right here? Is tilde given x sigma squared. This is going to be proportional to integral negative infinity to infinity. This one's going to be a normal. On x tilde, I'll write it like this. This is going to have parameters mu and sigma squared. And this is going to be the posterior distribution on mu given x and sigma squared. So this is problem 4. I don't mind solving the integral one more time if you guys can lock it down and know how to go through it. This is slightly easier than what I had done in class. So it is the same problem, but probably just all the notations blurring in people's eyes. So it's a little bit easier because this one right here we've done under the flat quadrant, where pi mu proportional to 1. And this is going to be ultimately pi mu given x. Sigma squared is equal to a normal centered in x bar, sigma squared equivalent. I don't mind doing that anyway. Little completion of the square, but I go backwards. Problem 3. This concerns maps versus MLEs. The problem is a maximum posteriority estimate, fancy word for saying maximize the posterior distribution. Give me the argument for maximum. Maximum likelihood estimators, same thing, but it's still a likelihood function. And they're only different by one term, and that's the prior values. And then this one, blanket.
Problem 1, part 1 is the end result of gamma.
That's your question. It is. Yes, it is. It's going to be a gamma. So, is pi phi given x a gamma? So, this whole thing was integral pi. I think we did it maybe like, I don't know, I mean, lots of ways to do a problem, but it really is just this at the end of the day. So I take my likelihood, multiply it by my priors. That will be proportional to this thing. Integrate over mu. One wants to know, is it a gamma? And it is. It has different arguments than the one I showed you before. It'll be an n minus 1 that should get there. So, but is it a gamma? Yes, it is. Yes. That's kind of cool. Conditionally, it's a gamma. This one's a different gamma, so you're just finding those parameters. And it'll kind of make sense to you. You kind of think about where would you think? I'll just say something about problem 4. What do you think expectation of phi given x should be? Well, I know I'm asking for a lot for you to guess, but can you intelligently guess about this? Let me ask this. If you wanted to estimate sigma squared, the way we normally do this is we write that on it. What do you use for that? The sample variance. Okay, so you might use something like this: sum of the xi's minus x bar squared divided by, yeah, maybe. So we have this conversation all the time. It never gets boring. But this is the unbiased estimator. That's kind of cool. So this is s squared. See this n minus 1 term kind of automatically pop up? What would you just, maybe? So, would you want it to be 1 over s squared? How would you feel if it were something like this? Would you like that? Feel pretty good. Aim for that. So that's a little bit of it. So aim for something like that. You're going to check your answer, see if you're in the ballpark, and see if it's that. I didn't say if it was or if it's not. Maybe somebody's already done it and knows the magical answer. It might be that. It might be something a little bit off. But you're just working over two different things in your gamma. Those two parameters that you're looking for. So you're going to do this by completing this one. Very, very similar to this one. Wildly similar calculation. Just in a kind of different context. This is normal, that's normal. We'll work through everything, and then I have to complete the square to do it. We have to do the same thing over here on this problem. So I'd say mechanically they're the same problems. If you want me to work through it, I could do that at the end. But really, it's the same math things, you know. But I kind of get it. In the beginning, everything looks different. It's all the same. But just to answer your question, and you can, depending on how quickly we get through this, you could say, carry on the details. I know Jenny wants me to just do it. So, not yet, not so fast. Let's think about it and see how we're doing. But yes, to answer your question, this is a given. Very well phrased question. Very easy answer. Again, you're going to be completing this one. So can we go through transforms? Can we solve this integral, maps versus MLEs? So, transforms. So I'll just write these other ones here. 3 maps versus MLEs. And solve this. Let's do the transformation thing. Now the question was asked in the context of the Jacobian, and we can talk about the higher dimensional analog, but everything happens for the exact same reason if you went through all these steps. But we have a formula. So our transform formula looks like this. And I always say things, it's the chain rule. So I'll try to explain that. Transformation of variables. Same note. X is, we'll say, we'll use f, I guess. F of x. I'll write down that this is the random variable of interest. Usually we make it different than the argument. It's the space everything lives in. X lives in this space. Say we have this formula. So this is a density. And I want to do something to it. Now I'm going to address one-to-one transformations. If it's not one-to-one, still apply the same formula, but we break up the spaces into regions where it's one-to-one. So if it's like going like this, a sine wave, you have to break it into chunks where everything is one-to-one, and do your mapping there. And there's a good chance that your resulting PDF is going to be piecewise. So express it with a big curly brace and say in this region it's this, in this region it's that. And if you've ever worked through one of those problems, it's not the funnest probably. Especially if you make a big mistake that you don't know. I've done that too. So, and you want to transform. Is this. I take g of x and I say that's y. This is my new random variable. So I've taken x and I've done something to it. And I'm going to say this is a one-to-one function. So essentially, if you tell me y's, I can give you x's. If you tell me x's, I can give you y's. So what that means is I can invert this function and I can write it down in closed form. So x is equal to g inverse y. And if this was a mass function, if this was like a Poisson, it's not a continuum, you're counting something. If I wanted to know what the new mass function is for this random variable, I just take this thing and shove it right in there. I see x's, I just call it something. Rephrase it in terms of y. But though that's not what we do, we have f of y, my new random variable. This is going to be equal to whatever this function is. So now I'm distinguishing between functions themselves. And I'm going to take g inverse y, throw it in there. This is feeling pretty good. That was just equal to x. But then I have this other term, derivative g inverse y. And I guess in a lot of probability books it just says that's what it is. And it's just like in your calculus class, and this is the transformation of variables. So when you're switching around the differentials, these cancel each other out, but there's a limit to it all. And they assume you know this. So they say you have this derivative that shows up just like when you're integrating and doing transformation of variables, but this isn't necessarily an integral yet. This is the function itself, how the function changes. And the way I've explained it so far is I say, well, this makes sense. You just plug that thing in. And then I kind of talk about this is how you stretch the space. Take the space and elongate it, morph it in just the right way, and this is what does that. And in high dimensions, if this was a two-dimensional problem, we need a bijective mapping of two variables, and this would be tiled with the derivatives, the 2x2 partial derivatives. So you have one of the functions with respect to y, one of the function with respect to y, the other function with respect to z, let's say that's the so on and so forth. And the absolute value changes into a Jacobian function. And it has the absolute value of the Jacobian function. Jacobian is, again, just measuring areas. So when you take the Jacobian and you write down the partial derivatives inside of this matrix, and then you take the, what's the word? Determinant of that thing. So that's what the Jacobian is you're taking the determinant of those partial derivatives, and then you take the absolute value at the end of the day. That, if you go back to your calculus class, that does just measure areas of spaces. We're not going to do that whole thing. I think we can just address this, and then we'll kind of scale up in our mind. This is what it is in height. This absolute value always shows up here. I remember somebody asking in one of the classes I had taken a long time ago, why absolute value? I understand the derivative thing, that shows up in transformation of variables in calculus class, but I don't remember having the slot in the absolute value. And a bad explanation, albeit it's true, is, well, it better be positive because these are density functions. But it feels very heuristic that if you say that. It's like, well, because of this rule. We want like can I just follow some math steps so you can figure out that needs to do that? So I think that's your question. So let's do it. So where does this come from? It's true, you just do it like this if everything's 1 to 1. But sometimes that's a negative sign and that might work. I'll show you where that comes from. I kind of promised you, this is just calculus, and it is. So let's just reformat everything just in terms of a calculus problem. So I've got f of x. We have that function. So I'm going to transform. And y is equal to g. This is going to be bijective. I can invert it. So let's just write down what the measure is. The CDF, the measure itself, this is usually what people call the distribution. You know, but then they are looser and it's like things are distributed as, and it follows this trend of PDF. And sometimes we more hard language and we say, that's the distribution. You can get one from the other, so it's fine. And I say that a lot. The measure, aka the CDF, where you're adding things up, i.e. you're measuring things in areas, is this. Fx, you usually write it like this, something like this, less than or equal to x. It's a convention. Usually we're always measuring things from the left side, or adding up left to right. There's no mathematical reason other than we have to take a direction to make it a convention. So that here we read left to right. I know in some places they read right to left. Some people read top to bottom. That would confuse the heck out of me, but simple rules that it's just a convention. So this is just a convention. What this is I'm going to integrate. I'm going to imagine everything in just real number line standard sort of model. This is this. And this is pretty abusive notation. So we probably want to just change up the notation just a little bit and maybe put squiggle on that. Because this is going to be a function of squiggle. That's squiggle. Usually we write it like this. So cap fx squiggle is that. We want to learn what's f g x is less than some squiggle. Remember, this is just a dummy argument right here. This is where I evaluate this thing. And almost always, I take that out. I'm like, well, I know they're all different. So
It should have there be probability
should be what?
The second F should be probability because it's the probability
Of the transform.
Yeah.
Exactly. So just explicitly, I've written this down and I didn't write this. Gidding's a math guy, so this stuff bothers him. He wants this one, and this is G of cap x.
I mean, you should use the notation of P probability here because it's
Oh, you want me to write P?
yes.
PR.
Yes.
That's fine. How about this? Because that's what it is.
No. PRX is less equal to X to the second one because this is the conventions in the probability terms.
Say what?
But the second one,
The second one, this one.
yes, usually use the PR then GX is less equal to X.
You want me to write this as PR?
Yes.
Okay.
But that's a convention.
I'll say we could do that. I could write that as PR. This means PR.
Right.
Cap F. Okay, and I understand. We've got all kinds of notations. So this is a probability. So you could write this out if you'd like. PR, G, cap X is less than or equal to X tilde. Does that make you happy?
Yes, awesome.
Okay, cool. So that's what I mean. And you will get this. It's like people that like to think about the spaces very abstractly, they want you to be more specific. We all appease getting by writing that down, but then I'm going to make sure we all know that's what it means. do the same thing all statisticians do. Can you forgive me?
Sure.
And I'm gonna get rid of that too. And just let this be implied that this is a random variable right here that I'm looking over. And I'm seeing if it's less than some whatever input function. It's gonna be an argument of this. So we want this. If I knew this, I could maybe answer this question as to what this density function is. So how did I move from the density to the measure? I integrate. So what's this right here? We're going to do the same thing, but I want to go backwards and go from this one and go to the density. So I'll differentiate. Do the opposite. And that's still, I still think that that's like pretty cool because I can only kind of do it like when I do the fundamental theorem of calculus. I can prove that those are anti-properties of each other, but I could never intuitively just explain that the tangent of a function is the inverse to the area under the curve. It's still cool. Yeah, I can prove that too. Okay, so we're going to first find this, and then we're going to take a derivative. So let's just write out what this thing is. I don't know much about this function right here, but I know a little bit about x. So we know this thing right here. I know something about the random measure for x. What will have it is I can invert this function right here. So it's invertible, so I can talk about this measure in terms of the random variable x, and I just invert g over to the other side. So let me just write that down. F of g, x, this is a probability. Don't be confused by my f. Is going to be less than or equal to x tilde. Is going to be equal to, this is 1 to 1. So g is 1 to 1. F x less than or equal to g inverse x tilde. So now I'm talking about everything in terms of the random variable that I know. Really all I've done is I've changed my integration values. So let's just carry this through. I know this. It's going to be the exact same thing that I wrote down before. So this is going to be the integral. Remember which little f this is that we're talking about, this random variable. I know its density function. So I'm going to integrate dx, but now I'm going to integrate between negative infinity and g inverse x tilde. And that's what it is. And you can always do this. You've got an invertible function, you don't want to do the transform, you don't remember the formula. It's as easy as just writing down this other thing and transforming over in the probability space. And this is still true, that's equal, no tricks. So now I want to get the density, F, and I'll say Y. Of Y. So we're going to differentiate. So that's this part. This is an equal. So I'm going to take my derivative with respect to x tilde. Getting.
Sorry, should you suppose that g is increasing here?
Yeah, I mean, it's still, I'm just saying that it's at this negative infinity bound. So when I do the fundamental theorem of calculus, this bound doesn't matter. So it won't even play into this.
And the g is not only the 1 to 1. It should be increasing function because otherwise you should fit the inequality.
Giving, I don't know if you're helping. So let's just leave it and we can have this offline. I'm going to do it the way that would be done in a rudimentary grad probability, not a measure theory. Okay?
I'm not saying about this. You should say that the g is increasing here because otherwise you should fit the inequality here.
I understand what you're saying. So I'm just gonna leave everything as it is right now.
Okay.
So integrate. You'll notice it doesn't matter what happens in this bound anyway. That's what we're missing. This is going to be G inverse X tilde F X dx. So we're about done. So how do I do this? Fundamental theorem of calculus tells me something about this. So in calculus class we learned I'm going to show you some examples so you can see where the negativity comes in and everything. Probably what getting's worried about. So we learned something like this, that let's say Z F something, I'll call it Y. This is just something arbitrary. DBZ, these are anti-properties of each other. I usually just write down negative infinity, but it can be anything you want. Z can only be there. If there was a Z down here, you need to break the integral into two pieces. You'll have this additive term. So what do? Plug in that argument right here. So that's the fundamental theorem of calculus. At least my version of it. These are anti-properties of each other. So they just wipe each other out. So you just evaluate the integrand with that argument. But if this was a function of G, we need to apply J. So I can also write down this is dz right here. That's 1. So that's that Z. We're going to do something very similar here. So F G inverse X tilde, that's our first bit. And now we've got derivative. Chain rule. There's no positive sign, right? It didn't happen. So there is no positive sign. It's just getting you to set up everything right. In which direction is everything going? Let's do a version where everything flips. And you do have some negative signs. You could do this with something like x squared if you wanted to do it, and then you've got the inverse process of plus or minus whatever we've set x squared to. So plus or minus square root of y. We have two integrals, we break it apart. We can look at an example like that. Well, let's just do something a little bit simpler. So let's look at a specific transform. So I might think everything's between 0 and infinity. So I might let x go between 0 and infinity, right here. And I've got some random variable. I've got its density function. And I want to consider y is equal to 1 over x. It's the only reason I'm dealing with that, so I don't have any new things going on. So I can transform this. This is 1 to 1, no problem. And so I could do the exact same thing that we did right here. So I could just look at probability. We'll go with Giddings notation this time. 1 over cap x is less than or equal to some argument. That's my cap f. So this thing right here is just integral. I don't know, because I don't know its density function. If I knew it, I'd just put that thing and integrate out to x tilde. But we'll just rework this. And I'm just going to rewrite this thing right here. This probability. Flip this thing around. So what happens? So cap x. So I've got my cap x over here, 1 over little x. I've switched the convention. I've complemented what I normally mean. So now I'm doing this increasing thing right here. We can write out what the definition is. Okay, I guess that's okay, no problem. It's not our typical notation. So if I wrote down that this is f of x tilde, it's not because I'm integrating from the other side. So that's that convention. That's where the negative sign comes in the absolute value. So let's just do this by hand right here. That feels pretty good. I'm going to now integrate between, I don't even care what this is. It doesn't even matter. That's what we're discussing. So I'm not even going to write it down because it's not even going to help me. But now I can think about this thing right here. And I'm going to integrate from 1 over x tilde, and I'm going to use x's density function, dx. So now when I go to do this, and I take a derivative, so my differentiation, that's why I'm saying, just give me a second, you know? So we get at least to the things. And if you want to butter it up a little bit, you'll be well prepared to be an editor of chat. You know, you can call people out on all this and shouldn't you write this, and it's totally fine. So I'll even say that that stuff is important. But I need to flip this around right here. So I'm going to flip it around so that I can do everything first. So this is going to be equal to negative 1 over x tilde. So these negative signs pop up automatically right here in these things where if the sign is flipping, it's flipping because of this. And it will always be positive. If you follow the fundamental theorem of calculus and you're integrating over these positive things, it should be positive and it will be positive. And the term will always look like this derivative term, but the absolute value sign is there for like when you flip around the space and you're now integrating in the other way. So this is going to be f of x dx. So when I take my derivative of all of this, dx tilde of my minus integral 1 over x tilde. Again, if there was an x tilde down here, you break it into 2 integrals. Take those endpoints 0 and just add it up to 0 or whatever that point is that's convenient for you. This will look like f x right here dx. Pretty ugly notation with a negative sign right in the middle. So I'll put a place there. Fundamental theorem of calculus. This is going to be f x 1 over x tilde. That's the inverse function that's getting plugged in here. And then derivative, 1 over x tilde. I'll write it down as x inverse. There's a negative sign in here. It's that one. So watch what happens right there. This negative sign comes down. And then I get a positive. So this thing right here is going to be minus x tilde to the minus 2. This negative sign will cancel that negative sign, and it will always be positive. So that's where the little heuristic trick of just always drop the absolute value sign on the derivative comes from. So if you're taking, and it makes it really nice because if you are working with Jacobians in higher dimensional spaces, you write down the tilings of partial derivatives, and you take the, what's that function? Determinant. You guys know if you take the determinant and you flip the columns, you'll put a negative sign in there. If you take the rows and you flip them and you permute them, you'll put another negative sign in there. So you can scramble them just as long as you take the whole column together, or the rows together. And so you never need to know, like, oh, what's the order you did the derivatives in. It's just as long as you're consistent and you're writing it down. And I won't ask you to do a hard multivariate problem where you need to come up with a Jacobian in class. Might be one on the homework at some point. It doesn't matter which order you're going to take it in, because you're going to take the absolute value at the end of the day. If you took this argument to a two-dimensional space, it'd be the exact same thing, and everything would turn out positive for you. It really would just be that Jacobian is the change. So, here's a quick heuristic, absolute value, because it needs to be positive. Why is it really positive always? Because it always will turn out positive when you're following the fundamental theorem properties. So, integrating over regions of positive space, it better be positive, and it is. How's that? Is that helpful? Cool. So now you guys can go teach this to graduate students that are coming in next year. They'll understand where this comes from. You guys know that already? More. Yeah, exactly. It's like, kind of, yeah, that makes sense. Depends on how much value you're getting to, right?
Yes. Same.
Yeah, exactly. So, nope. Next question. Maps versus MLEs. Question is, this one is, are maps invariant to MLEs? Or invariant to transformations? Let me just answer the question in general, though. Make that important. I've seen this in a talk before, where somebody took their map estimator, they transformed something, and they shoved that in, and they said it's the map. And it wasn't. It's not. It's just not. You know, it could have been close. It might have been, but it definitely did not apply in this case. So it's like, oh, back to the drawing board. Imagine giving that talk and somebody calling that out. It's not the map anymore. So. Embarrassing mistake. Easy to fix, probably. Okay, MLEs are invariant to transforms. So, and it doesn't matter what kind of transform. It could be non-one-to-one. It's easy to show in the one-to-one case, but it doesn't need to be one-to-one. I'll just try to explain this in an example. So, say you want, and this is true in just a general optimization problem. So there's nothing particularly fancy about this function. It's no special property that it's a likelihood. Special properties come in when we have measures on things. And again, it's that Jacobian. It changes everything. So, say we want to find the arc maximum, the argument that maximizes, I'll say, over sigma squared, and I'll write down some almost arbitrary function. I'll put my sigma squared inside of here so that I'm always looking at sigma squared. So when I'm playing around with the same variable, I like to write it the same way all the way to my function. This will look like e to the minus 1/2 x minus mu squared over sigma squared. So let's say I'm trying to maximize this thing. Say you know what mu is, and I want to find the max of it. And we know what this function kind of looks like at this point. It looks like an inverse chi-squared kernel, inverse gamma. So let's say that this was 5. Okay, so it means that after I went through my maximization algorithm, I found that the peak of this, i.e. I plugged in some data right here. I had whatever mu was. So I was able to plug all those things in. I was able to draw this curve. So this function looks like this. Right here. Something positive, and it peaked right here at 5. This will be the likelihood on sigma squared. So I gave you an x and a mu such that this works out. Now I might want to know the answer to a different question. So say somebody asks you, what's the MLE for v is equal to 1 over sigma squared? And we know the answer. This is what it means to be invariant transforms. I just flip that thing upside down. So when I see sigma squared here, I just plug in max sigma squared. So that's going to be phi half MLE. It's going to be, I'll call this sigma half squared MLE. It's going to be 1 over sigma half squared MLE. It's going to be 1 over 5. That's what it means. Let's see if we can convince ourselves that that's true. I know that this function peaks when this thing is a 5. But now I'm going to rewrite this in terms of 1 over v. When I see that, I rewrite it in terms of 1 over v. I know that this function peaks when that thing is 5. That's 5. So rewriting it in terms of 1 over phi, if I make phi 0.2, then this thing is 5. Because they don't peak at the same place. And in general, you can kind of just, I don't know, convince yourself that that's true. Where else would it peak? Why would it peak somewhere else? So if that's not true to you, go home and sleep on it and think about it and pull out math out and plot. See where it peaks, but it will peak the same place. So in general, for MLEs, if theta hat MLE is known, and we transform, and we change scale, I say transform. Let's say g theta is equal to psi, which will give us new arguments. Then if I wanted to find the maximum for this thing, right here, it's pretty easy to do. So psi half MLE is going to be equal to g theta half MLE. It does not matter if it's a one-to-one function or anything like that. You just plug it straight in. And that will maximize that. If you didn't know that about maximums of just arbitrary functions, that's okay. Measures are different. So we're integrating over those spaces, and that Jacobian can shift the space. We can move it around. So we have to be careful. So just imagine, and this is the example that I alluded to in class, here's at least some form of proof that they're not, in general, invariant transform. Say, my posterior distribution, so I did all this work, did a whole bunch of calculation, I had some x's, I told you what the likelihood was, I take the prior, and I worked out my posterior distribution, and it turned out it's a normal 0, 1. That's never happened to me in my life. I got a normal 0, 1. I always get normal 0, 1s whenever you standardize everything. But let's just say the posterior was normal 0, 1. So this is going to be true for any distribution function, that the maximums are not always preserved. So if we're integrating over those spaces, we have to be careful. If we're thinking about it as a random variable, we have to be more careful. The max, so I'll say the map for this. So this thing looks like this. It's a normal. It's centered at 0. It has spread 1. That right there is the map. So that's the argument that tells us where the maximum is. If I transform this, same thing that I said in class last time. If we transform to, I'll say, theta squared is equal to psi, our new random variable. So what that means is I'm going to have to transform this whole space. It sounds like a little bit of a hassle. So we want to find pi psi given x. And we want to find the arc maximizer. Over flat. This thing right here, it's not a normal 0, 1. We probably know what it is. Warren knows. So normal 0, 1 squared, they're chi-squares. So if I take a whole bunch of normal 0, 1s, I square them out and I add them together, that's going to be a chi-squared with degrees of freedom, the number of terms I just added together. So if I do it just once, it's going to be a chi-squared distribution. That's chi-squared. They're useful and they come up all the time. It's not really relevant. This is just an example to show you that the map isn't invariant. So let's say this thing, this is 0, map for theta given x. This is what it is right here. This thing is a chi-squared with 1 degree of freedom. And if you didn't know that, it would be a fun transformation problem to work that out. Try to work out its density. You can compare it to what you see in wherever you look for densities, Wikipedia maybe. Oh yeah, I came up with the right distribution. It should be a chi-squared with 1 degree of freedom. If you know anything about gamma distributions, there's a relationship to chi-squareds. They're constrained gammas. And we might see that later. But what we know is this is a maximized max at whatever the degrees of freedom are. Degrees of freedom for this problem is 1, so this is going to be maximized at 1. That is not equal to 0 squared. So if it were invariant to transforms, I could just grab my map, 0, square it, bada bing, bada boom. This is a counterexample. So what's left, other than the likelihood in a Bayesian analysis, what's the problem? So let me just write down and try to conclude a little bit instead of just leaving you with, maybe you should think about it some more. Let's just write it down. So posterior looks like this. It's going to be proportional to. Everything else is a constant. It'll be a function of x, so we don't have to worry about it. It doesn't have thetas in there. So this will be the likelihood function with x times the prior. This is a measure. We have to treat it as a measure. We need to treat the whole space. Even if it's improper, you have to do this. Even though you can't integrate over the prior specifically, that's where the randomness is coming. And so proportional to that. So say we have psi is equal to g of theta right here. So I could take just psi g inverse theta. Say it's 1-to-1. It won't matter in this case, but just so I can write this down notationally and make the problem easy, I'm going to assume this thing's 1-to-1. Get in a likelihood function, it does not matter. That's not what's making it peak in the same place. I'll let you just think about that. But what I'm going to do, that's backwards. So theta is equal to g inverse psi. So the maximum likelihood thing, from the likelihood, I can just slot that in and maximize over psi. I think the way I explain this in my inference class is, it doesn't matter if I want to just change the function right here. So I'll just write this down, that this is equal to likelihood g inverse psi given x. And then I've got this bit right here. So I'm going to talk about that in a second. So I'm not finished writing. So the contribution to the maximum from this, it doesn't matter if I move psi, I wiggle it around. I can find maximums by wiggling things around until I find something that peaks. Or I could move psi around. Or I could move psi and wiggle psi around. It doesn't matter. So I kind of think of this, and maybe this is a bad analogy, it's like gears turning to me. So I can take this other thing and I can spin it around a whole bunch of times and move something, and maybe that turns one big wheel around. It's like on your bicycle. I don't know. Mechanical engineers in the class? Nobody knows. Okay, so that's a great analogy. But I don't know. I think of it as just like gears or something, the rate at which I turn things. So I can wiggle psi, and it will wiggle theta form. This part we have to be more careful with. Because if I want to transform this, I need to take this thing right here, and I'll be specific and write a theta down there. Because I need to, like, pi theta, I'm going to rewrite in g inverse psi. But I'm not done yet. And that's the conversation that we're having up front. I've got this extra term. I've got that positive derivative thing. The g inverse psi d psi. So when will this be invariant to transform? Put my absolute value signs there. I didn't move it. All of this stuff right here, I'm just plugging straight into the function. I'm treating it just like when I, refine the MLE. So I'm just plugged and shoved into this. So it's when this part right here doesn't move the maximum. Again, this is the same parametric function right there. I'm just writing it in terms of a different parameter. It doesn't matter how I turn this. I turn it in terms of theta, or turn it in terms of psi. So it's really a question of, when does this have anything to do with psi? So if this is a constant, unswapify my board. If d g inverse psi, d psi is constant, i.e. no psi's appear. Then the map is invariant. There's no psi over here. That's it. So you gotta always think about this. So I guess the remainder of the question is when is this constant? Yeah, it's for linear functions. hyperplanes and stuff like that. That's when it's important. So if G is a linear transformation, then the map, you can just plug it into the old thing. Otherwise, you're going to have to probably redo your optimization. I guess that's good to know. Okay. So tempting to think that we can use this thing that we learned if we learned about MLEs. I told you what they are. They have some good properties, but regularizing it is a little bit better. So the likelihood is just one step from being a base. Okay. So I think I've answered that question. You can think of that in any number of ways. We can write it up whatever detail you want, but I'd keep this in mind. It's a very typical midterm question. So you'll work through it, show me some argument like that, and you can say this is constant when everything's linear, and I see the word linear, I can give you 100%. Okay, good. So I said a lot about that. So this, whoever asked that question about frequent, they're not here. But maybe it helped us all out. Okay, integral. Now, the student that asked a question about the integral isn't here. I could maybe, if you guys think we live in a democracy, kind of, we could do Warren's question instead and take it all the way. Or we could just answer this guy's question. We guys want. They're both exactly the same in terms of mathematical. You're doing the same steps. It's just different little notation for every little piece. So I consider them the same. Let's just answer his question. And you guys can see if you can work out which gamma distribution it is.
Okay, so which
Problem
problem is
4 is what he's asking. So student wanted me to work out this integral e to the minus. This is a little tiny bit harder. Warren's question, because you cannot drop the sigmas in here, right? And that might be the harder part. You have your sigmas or your phis, whatever shows up, you can't get rid of them in this part of the problem. You've got to carry those with you. Makes sense, right? Because it's going to be an answer in terms of phi. It's a random measure on phi that we're building. And this one is going to be conditional on this. So I'll write this down in its full-blown glory just so that I can make sure we're all on the same page. This is going to be f x tilde given mu sigma squared pi mu given x. It's posterior distribution. D mu, negative infinity. I'll write down the whole thing. Integral 1 over root 2 pi sigma. This would be a phi 1/2. I'm going to throw this away in a second, but for the question Warren asked about, he just asked, is it some gamma? Yeah, it will be. You can't toss this. You're attempting to do that. E to the minus 1/2 x tilde minus mu squared over sigma squared. And then I've got this part. This part was a normal centered in x bar variance sigma squared over n. Block wire. We'll write down the whole thing. One over root 2 pi sigma over root n e to the minus 1/2 mu minus x bar squared over sigma squared over n. So don't get rid of the sigmas in problem 1. as they're part of the answer. You can just get rid of those right here because we know sigma squared. So really the same mathematical steps, but there are some things you need to carry around in the other problem. And I would say it's exactly the same, it's just bookkeeping. We want to do this one more time. So I'm just going to write down this is up to proportionality because everything's conditional on sigma. So I always use the notation to tell me what's conditioned on so that I can know what I get to roll. So the reason I'm so pedantic about my notation and my conditioning is because it helps me remember what I can possibly roll. So this thing is going to look like proportional to e to the minus 1/2 x tilde. I'm going to do all my expansions up front over sigma squared minus 2 x tilde mu over sigma squared plus mu squared over sigma squared. I'll combine everything into the same exponent. So now I'll expand these ones. This is going to be plus mu squared. So over sigma squared over n minus 2 mu x bar over sigma squared over n plus x bar over sigma squared squared du. Again, integrating over the whole space. So I've already written this up to proportionality, and if I haven't thrown away the wrong stuff, I'll be in good shape. So this is going to be proportional to e to the minus 1/2. There's a couple terms I get to throw away. So can't throw away that, can't throw away that, can't throw away that. But I can throw away that. Because we know sigma squared in this case. So we know x bar, we know sigma squared. That can be factorized out, so it's a proportionality constant. And I'm factorizing out the equation. So this part, I'll just factorize out the x tilde e to the minus 1/2 x tilde squared over sigma squared integral. And again, I'm going to get rid of that last term. I'm going to combine my quadratics and my minus 2 linear because they tell me what this is all, what normal this is that I'm integrating over. So e to the minus 1/2 mu squared. I've got a 1 over sigma squared right there. And I've got a mu squared term over here as well. This would be 1 over sigma squared divided by n. And in 4th grade, we wouldn't let you write this. And in my class, you could write it. So minus 2 mu. Interchange those, just swap the order of them. Minus 2 mu, this will look like x tilde over sigma squared, and I've got this term right over here, plus x bar over sigma squared over n d mu. Question is what does this integrate to? I'm hoping this becomes, when we get to model selection and all of that, that this is autopilot for you. Does anybody know? So I'm just going to write this down, is this whole thing right here, the integrand, looks like a normal it has a couple of parameters in here. It's got a variance term. I recognize that is the inverse of that part. So this is going to be 1 over sigma squared plus 1 over sigma squared over n inverse. I'm going to call that V for variance. And again, some books will rewrite this a little bit different and write it over the same denominator and add that up. I don't really care. So if you're doing it on a computer, that would probably help you. So that you don't have so many divisions all over the place. But I kind of like this. And the expectation is going to be this term multiplied by that thing. So this will be E. And that thing is x tilde over sigma squared plus x bar over sigma squared over n times this thing. Most Bayes books will write this down, in kind of a more compact form. But I like writing it like this because you can see this is a weighted average of these two little pieces. So I like seeing that, and I like to write it that way when I teach. So that's E. So that could probably help you. So again, just as a reminder, integral 1 over root 2 pi sigma, well, I'll just write it down as this, e to the minus, and I'll just come up with an arbitrary variable, z, minus e squared over b, there's a 1/2 in here, dz, this is equal to 1. It's a Gaussian. I changed my argument to z. But I did use the same notation, e and d. I could have used a mu and a sigma squared and all that. But I know that integrates to this function. Integrating over just between negative infinity and infinity. So I'll just do a little bit of rearrangement. And I'll write this down as root 2 pi v. I hope I have that v inside of the square root. I don't know if I did a second ago. But anyway, it's like this. And so, and I'm going to rewrite this. Just as integral negative infinity to infinity e to the minus 1/2 z squared over b minus 2z e over b plus e squared over b dz. So that's the exact same thing. I'm going to focus on those terms right here. So I'm going to rewrite this again one more time. You can see e to the minus 1/2. And on the left-hand side here, I'm just going to focus on these terms. Z squared over b minus 2z e over b. I'm just going to leave those. And I'm going to rewrite this one right here is e to the plus. Keep in mind, that's plus, that's minus. So when I swing it over on the other side, and I can do this because I'm integrating with respect to z. This is the only term where z doesn't appear. Plus 1/2. This is going to look like e squared over b. That's what this integral is equal to. You could have done this a different way, and they're exactly the same. You could start with this thing that we have. I can complete the square. I can factorize the thing out that I had to add and subtract. Factorize it out, and it's going to be exactly the same thing at the end of the day. if that helps you to do it that way, I don't think it actually takes any more or less time. Just like this, because it's just auto. So this integral is something that we can figure out. We have a name for E, we have a name for V, but it really is going to be just this part. Right here. So let's just do that right here. And get rid of this. This is what I want you to remember. Square root 2 pi, you can actually always toss that. Sometimes you have to be careful with the variances. Hold on to it. We'll see in this case if we do. In your problem, Warren, when you're figuring out which gamma, you're going to need to hold on to that variance. That's what's going to make this a little bit different. It's going to have arguments in there that you can't just plug. So if you don't come up with the right answer, it's probably there. That's what I'm guessing. So this will look like, this whole thing now is going to look like e to the minus 1/2 x tilde over sigma squared. Squared. E to the plus 1/2. And it's going to be e squared over v square root 2 pi v. Let's just write it out and recognize what this distribution is. I know what that variance is. So what we just wrote down is e to the minus 1/2 x tilde squared over sigma squared. E to the plus 1/2. We'll write it down as x tilde over sigma squared plus x bar over sigma squared over n. This is E. Hold on, I'm not done with it yet. E 1 over sigma squared plus 1 over sigma squared over n invert squared, and then I have to divide by my variance. So that's the e squared over v term. So it'll be 1 over sigma squared plus 1 over sigma squared over n inverse. So lots of bookkeeping, because that's what d is. And then I've got my square root 2 pi 1 over sigma squared plus 1 over sigma squared over n invert right here. Notice in all of this, I know n's, I know sigma squareds. So again, my answer is only is this right here, of the proportionality. I don't need that. Problem 1, you need that term. So again, just kind of nuanced bookkeeping. Now I need to recognize which distribution this is. I know it's a normal. It's a question of which normal is it. So let's just carry out the steps, because I think that's the student's question. See if we come up with the right answer. So this is going to look like e to the minus 1/2. I'm always going to call that outside. And what I want to do is I want to write this down in terms of two terms. There's a bunch of junk floating around, but the only parts that I really care about are, where's the x tilde? What's multiplying next to it? So where's the quadratic term in x tilde, and where's the minus 2 linear? So this is some normal. Those iterated forms are seeming really cool all of a sudden. Let's see if we get the right thing. So this thing right here is an invert of that We've got one down here as well. How many of those do we have lingering around? It's kind of fun. So remember what this thing looks like right here. So this is going to be E squared divided by V right here. And then, so this is just E squared divided by V with all of this. I guess we'll just work it all out. So I've got one downstairs, one there, it's being squared. So X tilde squared over sigma squared minus that plus, and I'm soaking the minus up right there. So there's some subtraction in here. Let's just write this out. X tilde over sigma squared plus X bar over sigma squared over n squared. This is going to be divided by 1 over sigma squared plus 1 over sigma squared over n. I probably should reintroduce some notation for this pretty quickly. So this is going to be minus 2. And then I have this other one right here. It's appearing. I've got another one downstairs. You guys see that? So all I bring to this part, and then I have this other one. So there's a third one down there. Everybody agree? So this one is squared. Boom. Got this one. And then I've got the other one. They're all over the place. Let's just make sure we're right. So let's just make sure we got it right. So this one is minus 2, but then I put it down here. So I'm dividing. So I made this one plus 2. And then I've got this one, which is a minus 1. So we're off by a negative sign. So this right here was squared, and then I have this other one that I need to bring in. That's minus 1. So, minus 1? Plus 1. Plus 2 minus 1. That's where it's like, I know how hard it is to stare at a chalkboard. So this is the stuff that you make get really good at. That's a 1 right there. This one went downstairs. Reverse the sign on it. So I like that. So there's some cancellation right there. So a little bit of niceness. You start seeing negative 3s pop up in things, you probably know you've never seen that before. So let's just keep solving all of this. So this is e to the minus 1/2 x tilde. And what I'm going to do is the same thing that I always do. I just expand everything out. Keep track of everything, find my quadratic terms, my minus 2 linear terms, and then I'm done with the problem. You'll see now why I don't like doing it all the way through this. So this is going to be minus, this will be x tilde squared. Just give me a second. So I want to not set fault on this. So I want to see if we can maybe do some factorization on this. I don't know what the cleanest way to do this is. I'm really tempted to rewrite this thing and get some cancellations in the sigmas here. It'll work out either way. So let's just do that. So x tilde sigma squared, let's just write these out as squared terms right here. Plus x tilde x bar. It's going to be sigma squared over sigma squared over n. Right here. There's two of those. Plus x bar over sigma squared over n sigma squared. 1 over sigma squared plus, I'm prepared to pull that n upstairs now. I'm starting to get tired of looking at it. So we're almost done. So now I just need to rewrite this in terms of x tilde squareds and the linear term. So e to the minus 1/2. Which term can I get rid of? It's that one. So I don't need this. I can factorize that out of everything. Doesn't have the x tildes in there. So x tilde squared. We're going to figure out what that's multiplying next to. And then I'm going to look at the minus 2x tilde. There's a little hint, that better be a minus sign that shows up. I need to look at what's multiplying in there. So let's do it. I've got 1x tilde right here. This is a 1 over sigma squared. Then I've got another one right here. So that's going to be, giving myself some room. This thing right here is going to be 1 over sigma squared. We're going to have another one right here, plus 1 over sigma squared. Yes, sir. Minus. I just was looking to see if I missed an n here, but I didn't. So sometimes I try to check as I'm going. So minus squared, and then it's going to be divided by, I'm just going to rewrite this as 1 over sigma squared, right here, times n plus 1. We'll have to work on that in a second and simplify. Maybe simplification along the way would have helped. And now I need the minus 2 linear. So good news is that thing right here turns that into a minus. So we're good. So minus 2x shows up. This is going to be x bar. It's right over here. X bar over, we've got sigma squared. We've got another one, sigma squared over n, right here. And then we have this other thing right here that it's all dividing into. So this is going to be 1 over sigma squared, and there's going to be an n plus 1. Getting? What's good? Yeah, exactly. I love the attention to
You can use
detail now.
you can use multiplication instead of.
Yeah, I probably should have. Okay. So with some luck, this will actually work out. So let's just work on the variance here. So this is our variance, and I'll tell you which one it is. Variance of x tilde given x, and sigma squared. It's equal to that, and this is the expectation of x tilde given x over sigma squared. That's just simplified, but it's starting to look pretty good. Doesn't look good, does it?
First, you should do the inverse of the variance.
Oh, yeah, right, this isn't the expectation. This is the expectation times, I need to multiply by this variance right here. So this is gonna be this term, this is inverse, and I'm gonna have that variance inverse here. So we've got more work to do. Let's get rid of this. So our variance, let's just work on that one first. X tilde given x, sigma squared. This is going to look like, one of these is canceling right there. So I've got 1 over sigma squared minus 1 over sigma squared. And this is going to be n plus 1. We need to invert this thing, put it on the variance scale. So I can n plus 1 here, n plus 1. Starting to feel pretty good about this. This is going to look like n plus 1 minus 1, so this is n over sigma squared n plus 1 invert. So this is going to look like sigma squared n plus 1 over n sigma squared 1 plus 1 over n. That's the answer. And that is right. That is what we wrote down last time. Which one? We'll write this one down in a second. So far we've just been chewing on that. So we looked at the quadratic term. It was this. So I just wrote this thing down upside down, inverted it, and it turned out to be that. Now let's chew on this. Okay? And I've got to answer your question. So this looks good. Now that we have this is our variance. Our expectation, this is what Jenny's asking. It's going to be all of this junk right here. And I do hope that we got it right. So what we wrote down. So this was x bar. We know what the answer is supposed to be. You guys know what it is? We'll see if it makes sense in a second. So x bar. This is going to be over sigma squared. Over sigma squared divided by n. This is going to be one over sigma squared n plus 1. And then I've got this thing right here times whatever my variance was at the end of the day. Multiply that minus 2 linear term times that. Sigma squared 1 plus 1 over n. This one will cancel that. This one right here cancels that. This was the inverse variance, right? No, it wasn't the, it was the inverse of the quadratic term. I got it. So multiply this thing through. This n goes upstairs. So I just took that n from there and threw it up here. I'm going to multiply it through right here. N times this thing right here. N plus 1. And with Ying's help, I can do this anyway. And all of you guys making sure I'm taking care of everything. What's left? X bar. That probably could have been tidier if I did some bookkeeping along the way. But let's just remember. So we did do that right. That's good. I feel good about myself after 15 years of teaching at Virginia Tech. I can still do this. So there were things that I thought I could only do in my first year of graduate school, but I can still do them. Let's just remember in this problem. So I asked you to do this because I want you to walk through these exercises. Go through it, and then you'll reappreciate what we had done in the first place. This was expectation of the expectation. X tilde given mu x sigma squared. So I'm always really heavy-handed with all of my conditioning, so I can just remember. So given x is sigma squared. So this is the expectation. If I know mu, those won't help me. So this is expectation of mu given x is sigma squared. This is the posterior expectation, and we already figured that out as x bar. We get a lot of work to get that exact same answer back. X bar. So just keep in mind, these are intervals you're solving. So those expectations. The variance is similar. I'll write it up here. X tilde x sigma squared equal to the expectation, the variance, x tilde conditional on mu, my data, sigma squared, conditional on x, sigma squared, plus the variance of the expectation. X tilde given mu x sigma squared given x sigma squared. Expectation of the variance of this, and I get to know the variance. Perfect, sigma squared. And let's get our conditioning in there just so we know the obvious. Expectation of sigma squared, when we know sigma squared, sigma squared. So plus the variance of expectation of that is mu, conditional on x and sigma squared. So this is going to be sigma squared plus sigma squared over n. Variance of the posterior. Is that true?
So how is it that this values the expectation of mediated or linear?
Say it again?
So over
Yes.
I expected that expectation of x tilde at the is just expectation. It turns out it's expectation.
Keep in mind, I've conditioned over here. So I'm going to carry that conditioning everywhere. So they're all just have that conditional form. So let's just do this to make sure. You know this. you know, with the expectation of x tilde is equal to the expectation. I'm going to give myself a little bit of room here. Is equal to the expectation of x tilde, and I can condition on any random variable. We'll say we always pick the right one to make our problem simple. So that's my thing. Give myself a little bit more room. So that's true. You agree with that? If I condition on something here, Z, I need to carry that conditioning everywhere. That's all there is to it. I've conditioned here. This is true if you condition every layer and you carry that conditioning here. Remember, you're conditioning on something that's no on the left-hand side. So that same thing should be no over here. So you've probably just never written it down this way and had all this extraneous notation. But I assure you in this right here, when you get to like a step like that, writing down sigma squared over here is helpful. Otherwise you're like, is that the posterior that I need to find? Your notation would say that and you might confuse you. So you get to know sigma squared. So Jenny, if you condition on the left-hand side, you need to carry that conditioning in every layer. I always write down all that conditioning. So just as a quick follow-up, Stephen had asked me this earlier. So this was a good question. Thank you, Stephen, if you're listening. We oftentimes want something like this, right here. This posterior distribution. This is going to be the integral of x tilde, given whatever my parameters are. This is the way I taught this to you. So we integrate over all of this. Stephen came in and said, isn't it really this? Because you conditioned here. Don't I need the condition right there to carry that conditioning through? And he's absolutely correct. Yes. But given I know theta, that data doesn't help me to do anything. So this is conditionally independent of that x. So what I'm saying is that they are the same things. I could write that x down, but you don't actually have anywhere to plug it in it. You don't learn from it. If you know what the process is, yeah, it doesn't help you. It's the thing they do to you in Vegas when you go play roulette. They show you all the draws. You already know the probabilities of the table. So they are just baiting you psychologically. Oh, there's 5 laps in a row. Probability of another red, that happens highly unlikely, but given that you know the probabilities of the table, you shouldn't even be looking at that little thing. They figured out a long time ago, if they put board on there in the historical record, that gets more people to try to outsmart the system. Just outsmarting themselves. So same thing right here. So that x would go here. If it's conditional on the right, you need all that same conditioning carried through. But in some cases, things are conditionally independent. You're more than welcome. You guys want to get out of here? Jen, one more. No, the smiley face is the thing that goes away, right?
So how is it that everything doesn't go?
Okay, so let's do it again. So I wrote down this one. Expectation, x tilde, we want this one, conditional on sigma squared. Expectation of the expectation. X tilde, my smiley face is now going to be mu. That's smiley. So this is x and sigma squared right here. You don't actually need this x, it doesn't help you. This is going to be conditional on x and sigma squared. So these ones are my z. That's what I'm calling z in this format. and that's the same thing. This right here is the sampling distribution of x tilde given mu. So this is the expectation of x tilde given that I get to know mu. I also get to know the data, but it doesn't help me. I have a presence of parameters. I can get rid of that. And I know the expectation of x tilde given mu. Remember what this is? Mu and sigma squared. This is a normal centered at mu. Sigma squared. It's a normal distribution. So again, understanding what the random variables is the answer to this. So this is x tilde. Okay, that's a forecasted point. That's just one point. It's normally distributed. Data doesn't help me because I get to know these things. And the expectation of a normal distribution, given you get to know where it's centered, is u. That's all it is. Why don't you go home, play around with this in a hierarchical fashion? Does this sort of make sense? I think just working through a couple of these in an inference book, kind of looking through a hierarchical model and seeing how to apply it, but it naturally appears here. Because there is this hierarchical model. Posterior, they're in the sampling distribution. So again, it's like you need to know what this represents. What is this thing asking you? This thing. That's what it is. Anything else you guys?
How do you sampling on problem 2, part 3?
Is that the one just with the gamma?
Yes.
So that, I guess somebody did ask that question.
They said after problem 1.
So is it, I think it's, I first want you to figure out what the gamma is, right? And so the answer to that for to be a T1 is a gamma half-half, is what you'll come up with. So what you do is you sample, I don't know, whatever you want to call it. Did I use lambdas or something like that?
Yeah.
So I think I wrote this. So this is just to get you out of at least just thinking about posterior predictives or whatever. This applies very generally. So if this is a gamma half-half, that's what you'll work out. You'll work out the map so that you know those are a half and a half. If you know what a t-distribution looks like, you'll be able to figure that out. And then I think we said x given lambda. Just to make sure I've got the right problem. This is the code sheet problem, right?
Yeah.
Okay, so this right here is going to be a normal. I don't really care what these are. Did I write it out like this? Sigma squared over lambda?
So it's a sample y, error left arrow, p of y given lambda.
Let me just look real quick.
So it doesn't say what
Yeah, exactly. So I'm just following this same scheme. Yeah, exactly. So I used kind of a slightly different notation for it, and I didn't write everything in, but this is what I mean. So equivalently, I mean this right here. So I could have written this down as this is f of x given lambda. You don't need to pick these to be, you can pick this to be 1, and this to be 0 if you want. I don't think I tell you what those are. You're probably to just pick those to be whatever you want. I won't be able to tell anything. So unless I really look at your samples, but looking at the min and the max, I won't be able to see anything. You'll come up with crazy answers and just wrote down wildly crazy answers. I wouldn't be able to. If you wrote down something that wasn't positive and negative, I'd probably go, that's highly. But what I'm saying right here is, this is what it is right here. So you're going to take this from a gamma distribution, you're going to grab that thing, you're going to plug that in for the inverse of the variance. And that will create a Cauchy distribution. That's gamma half. So I kind of just diced up the notation and wrote it in a more general way. The very specific ways of this. So this is acting like phi right there. You'll come up with stuff that looks good. So if you plot a histogram of it, it should kind of look like it's centered around wherever you centered this. Kind of have some diffusion according to whatever you pick there. So if you pick this to be bigger, it would make it bigger. But dividing by this, remember it's blowing out this variance. So as soon as you sample a really small value here, it's going to blow this thing up and shoot something way down on the tail. So it's equivalent to T1 distribution. That's kind of. I will point out real quickly, if you go to R and you input a half-half, just by default, it always thinks you have this on the inverted scale. So, kind of 2 right there. So type in your help, R gamma, and it'll tell you how they parameterize that. Cool. That's it, you guys? Last one.
This has to be recorded. So important. Is that right?
Yeah, so you're going to do this. So problem 1, first part, is going to be this. I'm not going to do this whole integral. I'm going to let you do it. But this, once you get into the hang of this, and this is just probability theory, there's only one way to get this, and it's to integrate over the joint distribution. So this will be equal to integrate over the joint of phi mu given x, phi mu. What's this thing? We can just write this down as proportional to, so that's where all the kernel stuff is going to live. So this is just going to be the likelihood. So I'm going to write it like this. Phi to the n over 2. That's what happens. E to the minus phi sum I goes from 1 to n. Xi is minus mu squared. There's a 2 in here. I'll put it over here so I can recognize it. Then you're going to have your priors. I think I say just use that. It makes you feel better to write the 1 in for mu. There it is. G mu. So you're doing this integral. Same thing that we did on the last integral. Remember, we're going to do the completion of the square thing. Recognize which normal that is, but make sure you carry all your p's around with you. You don't get to throw them away because this is the distribution. And then you'll recognize this is some gamma. Cool. I don't know how you instantly see that it is. You can probably see it that there's going to be this phi to the n minus 2 minus 1. That kind of looks like something. There's going to be some more ph's that pop up. There's another phi that pops up in this square root 2 pi variance term. That'll have something to do with phi. I guess you could have argued, well, I'm going to factorize out this phi with the sum of the xi squareds and see that it's going to be a gamma. But there's a whole bunch of terms that you're missing without being squared. So again, you're going to do this exact same integral as we did the last one. I'll do a step for you. This is going to be phi to the n over 2 minus 1. You'll get some more ph's out of this. So this is going to be, I'm going to do it in my head a little bit. So e to the minus phi sum of the xi squareds over 2. Now what's going to factorize out? Integral right here. This is going to be, remember this xi squared minus 2 xi mu plus mu squared. So I've got those to drag my sum across and everything. So this will look like e to the minus phi. I'm going to have, I guess I'll carry the 2 right there for now. This will look like sum of the xi's. I can factor the mu outside. There's a -2 in here. Sum of the xi's. There's a mu in there as well. Plus n u squared. U squared is constant in here. I'm going to sum it n times. This sum is just acting on here. D mu. So you've got all kinds of work to do. You've got to recognize which normal is this. So I would drag this V across back in here. Keep in mind, that is a negative sign sitting there, so an easy thing to mess up. You just put a circle around it. So you're going to recognize which normal this is. You're going to recognize the variance by looking at this term. So it's going to be the invert of that. The expectation is going to come from this thing. There's all this stuff. You're going to have the twos pop up in there. You might want to recall this something like x bar times n. Brings up that sum notation. The expectation of this will be this thing times the inverse of that. The integral will be e to the plus 1/2 that e squared over that variance term. Now you've got everything written down in terms of phi. Now is the time to recognize everything in terms of what we usually call everything. S squared does pop up in here. So just keep in mind, when we write out S squared, this might be helpful for you when you're going to recognize which gamma this is. Sum of the xi's minus x bar squared over n minus 1. This is the sum of the xi's squared minus 2xi's x bar plus x bar squared over n minus 1. So I'm going to write this down as n minus 1 times s squared is equal to this thing, which is equal to sum of the xi squared minus 2 times, I'm going to drag that sum across right here and recognize sum of the xi's is x bar times n. This is n x bar. There's another one. So that one gets squared plus x bar squared. N. And so we've got some simplification. This is sum of the xi's squared. We've got minus one of these plus one of them. So this is going to be minus n x bar squared. You'll recognize those in your exponents once you do this. You'll see that up here and you'll re-recognize how that has something to do with s squared. And that should be more than enough. Cool. I'm going to shut off the camera. Thanks, Jim.